Good morning, everyone. I want to start with a question that sounds absurd. What if I told you that building more roads doesn't reduce traffic? It actually makes it worse. This isn't science fiction. It's a mathematically proven phenomenon called the Braess Paradox, and it's been confirmed in cities around the world. Over the next 20 minutes, we're going to explore why our intuition about traffic is completely backwards and what that means for the cities we're building tomorrow. Here's how we'll proceed. First, we'll define the paradox and understand why it's so counterintuitive. Then we'll walk through the classic network example that makes it click. After that, a brief history. This idea is older than most people realize. Next, we'll look at real cities that prove the paradox by removing highways and watching traffic improve. Finally, we'll expand beyond roads to see where else this pattern appears and what it means for urban planning in 2026 and beyond. Let's start with the core idea. The Braess Paradox states something that feels wrong in your gut. Adding capacity to a network can slow everyone down. It's not a theory about bad drivers or poor planning. It's a mathematical inevitability that emerges whenever self-interested individuals share a network. And the flip side is even stranger. Sometimes the fastest way to unsnarl traffic is to close a road entirely. We'll see real examples of this shortly. So what exactly is the Braess Paradox? Formally, it's the observation that adding one or more roads to a network can slow down overall traffic flow through it. The mechanism is subtle. Each driver chooses the path that looks fastest to them personally. Every single one of those choices is rational. But the aggregate result, what mathematicians call the Nash equilibrium, is worse than if a central authority assigned routes. Arthur Pigou first noticed congestion externalities in 1920, but it was Dietrich Braess who crystallized the paradox in 1968. The profound implication is that we cannot trust decentralized self-interest to optimize shared infrastructure. Let me walk you through the classic example that makes this crystal clear. Imagine you're driving from start to end. There are two possible routes. One has a short fixed segment followed by a segment that gets slow with traffic. The other reverses that pattern. With 4,000 drivers, the system naturally balances, about 2,000 on each route. Now imagine a city planner adds a shortcut, a brand new zero-cost road connecting the two midpoints. Drivers immediately see it as a better option. They all take it. But here's the trap. By funneling everyone through the shortcut, they overload the segments on either side, and the equilibrium settles at a point where every single route is slower than either of the original two routes were. The road was added, and everyone lost. This slide captures the central tension at the heart of the Braess Paradox. On the left, we have the Nash equilibrium. Every driver acts in their own best interest. Nobody can improve their situation by changing routes alone, so the system is stable. But stable doesn't mean optimal. On the right, the social optimum, what we'd get if we could coordinate everyone. The difference between these two states is what economists call the price of anarchy. In a Braess network, that price can be surprisingly high, and the cruel irony is that adding infrastructure can widen the gap rather than close it. Now let's trace where this idea came from. It's a story of an insight ahead of its time. The paradox was buried in a German-language mathematics journal for nearly 4 decades, read by almost nobody outside a small circle of specialists. It took until 2005, the era of Google Maps and widespread traffic modeling, for the English-speaking world to discover what Braess had proven on a chalkboard in 1968. Let's walk the timeline. In 1920, British economist Arthur Pigou identified the underlying mechanism. When individuals don't bear the full cost of their congestion contribution, the system degrades. But it was Dietrich Braess, a mathematician at Ruhr University, who proved the specific paradox in 1968 in a paper titled Über ein Paradoxon aus der Verkehrsplanung. For decades, it remained obscure, a theoretical curiosity. Then, in the 1990s, with the rise of computational traffic modeling, researchers began confirming that the paradox wasn't just possible, it was likely in realistic networks. The English translation in 2005 was a watershed moment, and by the 2010s we had undeniable real-world proof from cities that actually removed highways. Let's spend a moment on the man and the paper. Dietrich Braess was not a transportation engineer. He was a pure mathematician working on numerical analysis. His 1968 paper was remarkably short, barely a few pages, and written entirely in German. For context, it was the height of highway building optimism when cities around the world were carving expressways through neighborhoods, convinced that more asphalt meant faster commutes. Braess's counterintuitive proof sat quietly, almost ignored, for 4 decades. When the English translation finally landed in 2005, it landed in a very different world, one dealing with chronic congestion, armed with GPS data and simulation tools. The paper's timing, ironically, was perfect. It arrived exactly when cities were starting to question whether the highway era had been a mistake. This is where theory meets pavement. For decades, skeptics dismissed the Braess Paradox as a mathematical toy, interesting in a seminar room, irrelevant in a real city. Then, several cities actually tried the unthinkable. They demolished major highways. The results were stunning. Traffic didn't just redistribute. In many cases, it simply disappeared. Let me show you the most famous example. In 2003, Seoul did something radical. They demolished the Congestion elevated highway, a 6-lane expressway carrying 168,000 vehicles daily through the heart of the city, and restored the buried river beneath it. Critics predicted paralyzing gridlock. Instead, the opposite happened. Traffic in the surrounding area actually improved. Drivers adapted, they changed routes, shifted travel times, and many switched to the expanded public transit system. Meanwhile, the restored river became one of Seoul's most beloved public spaces, attracting millions of visitors, spurring business growth, reducing the urban heat island effect by up to nearly 6 degrees Celsius, and increasing biodiversity. It is the Braess Paradox made visible, a real-world demonstration that removing capacity can heal both traffic and the city. Let one number from the Seoul case sink in. Nearly 6 degrees Celsius. That's the reduction in the urban heat island effect in the neighborhoods around the restored Cheonggyecheon stream compared to parallel roads just 4 to 7 blocks away. But the benefits went far beyond temperature. Air pollution dropped. Biodiversity surged. Species that hadn't been seen in central Seoul for decades returned. Property values rose, businesses multiplied. Public transit usage increased. And crucially, traffic did not collapse. The highway's removal didn't just avoid the disaster skeptics predicted, it unlocked a cascade of urban improvements that the old elevated expressway had been suppressing for decades. What makes the Braess Paradox so powerful is that it's not really about traffic at all. It's about networks. The same mathematical structure appears in electrical grids, where adding a transmission line can create new paths for power that destabilize the entire network. It shows up in biology, where metabolic networks with extra pathways can become less efficient. On the internet, adding more peer connections between ISPs can increase latency. There's even an analog in sports. The Ewing theory, named after Patrick Ewing, suggests that a team sometimes performs better after losing its star player because the offense becomes less predictable. The common thread? Whenever independent agents optimize selfishly on a shared network, adding options can make things worse. So what does this mean for the people designing tomorrow's cities? First, we need to retire the intuition that more asphalt equals less congestion. Decades of evidence, from the Braess Paradox on one side and induced demand on the other, tell us that expanding road capacity in congested urban areas is a losing strategy. The winning playbook looks very different. Audit existing road networks for links that might be causing Braess-style traps, invest heavily in alternatives to solo driving, and use congestion pricing to bring individual choices in line with the social optimum. Cities like London and Stockholm have shown that pricing works, and before any major infrastructure decision, run the simulations. The math exists, we just need to use it. Let me leave you with 5 ideas to carry forward. 1. The Braess Paradox is real, mathematically proven, and empirically confirmed. It deserves a seat at every infrastructure planning table. 2. Seoul and San Francisco didn't just survive highway removal, they flourished. 3. This isn't just about cars. Any network with selfish routing is vulnerable. 4. The solution isn't to stop building, it's to build smarter, with tools like congestion pricing and rigorous simulation. And 5, perhaps most importantly, the paradox teaches us humility. Complex systems can behave in ways that mock our intuition. The best road you can build might be the one you tear down.